Good morning. So, some technical difficulties, first track here this morning, and I have to remember not to walk in front of the projector. So, I'm here to tell you about the security alarm. I was a bit worried trying to get it into the country, but here it is. Nice little metal box. So, this is me. Those of you who don't know me, I work at Possible Security. I'm lead researcher there. We do pen testing, consulting, all the usual stuff that a company does. Now, I do spend quite a lot of time with my hobbies, though. Let me click this here. Oops. So, network flow analysis is one of my hobbies because I moved into IT security from networks, from computer networks. In this case, this is an alarm network. It's a different kind of network, but I have analyzed it nonetheless. Reverse engineering, also one of my favorites. I'm working on reverse engineering thing as well. Social engineering, legal dimension, and please do follow me on Twitter. I tweet a lot. It's all in English, so IT security stuff. Now, I don't think so, but do we have any people in the audience who have seen the previous version of the talk? Oh, okay. Well, luckily for you, I included 2 topics from the previous version. So, general alarm system intro and about the Paradox Systems, the company that made this not so highly secure device. But I also added new stuff, of course. And the research that's been carried out between last November and today is I dug into the remote protocol a bit. So there's a nice remote that you can click to actually arm and disarm the system. I was planning to present a demo on that as well. But unfortunately, as I understand, India doesn't like unlicensed ready devices in their country. So, but I have other demos for you. But so I'll show you some specs for the remote that I discovered. Then I also made an attack tool. Now, in previous version, we had to have a laptop, we had to have a whole rig to actually attack the system. In this case, you will see it on the screen, I hope. When the demo comes, I made an attack tool that is a small 5 by 5 centimeter box that you can actually use to attack the system. And I also looked at firmware reverse engineering. So I tried to understand, is it easy for this specific device? Will I be able to reverse engineer the firmware? And if not, what else can I do? Security alarm systems in general, right? Just a definition here. What I'm talking about is a system you can have in your office or in your home where you put a chip card or you put a PIN code and it locks down. The alarm sounds when someone enters, right? And security alarm systems have gotten pretty good in preventing bad guys from getting to your stuff. Here's an example of a security alarm system that is equipped with special devices that produces smoke when alarm is tripped. And as I say, you can't steal what you can't see, right? So depending on the configuration, security alarm is what actually stops the attacker, right? I don't know how it works in India. In Europe and the States, usually security alarm system is installed by a third party, by a company, which means they also go to the site and try to arrest whoever is doing the bad stuff, right? But it usually takes some time to get there. Driving from the airport to here, it took me like more than an hour, for example. So what could go wrong with an alarm system? One of the things that could go wrong, you have your code, right? The code is usually 4 digits. It's relatively short. So if attacker were to try many possible codes, he might end up with getting the right code eventually. How many of you have worked, and I mean used, with an alarm system in the past months, like at work or at home? Anyone? Okay, like 4 or 5 people. Oh, a bit more. So if you've ever entered the wrong code, like 5 times, you will be in trouble, right? Maybe some of you have experienced that. System will lock out and will not allow you to guess the code. But here, if it is done by a robot, let's say over a period of 30 days or 60 days, the robot can do that slowly enough as to not trip the protection of brute force. Another thing, let's look at this example here. We have a storage building. It's a large building, or it may be a hotel like this, right? But hotel is a public place, so your private house, but it's a huge house, or a storage building. And you have installed an alarm in it. You have, of course, your keypad at the entry. You have, of course, one more keypad because it's a huge building and some of the people enter from different direction. You don't want to walk all around the building, right? I once stayed in this hotel in Tallinn and the hotel is literally 900 meters long. And if you get to the wrong side, you can't get in, because the entrance is only from the other side. So for large buildings, it is not unusual to have an extra keypad installed on some other places. And we, of course, have different sensors. Those can be passive infrared sensors or sensors that trip the wire when windows open, and so on. Now, let's say one of the keypads is not really used. It's there, you installed it, but no people actually use it. So what that means is it's abandoned. It still works. You can still use it to access the system, but no one uses it daily. So what happens if an attacker gets access to that keypad? Can the attacker do something bad, like exfiltrate information about your movement, about where you are in the building, about where the sensors are being tripped? Or maybe can the attacker exfiltrate a code that you're entering on the other keypad? So that's what I'm going to show today, just part of what I'm going to show today. So Paradox Security Systems, right? It's a Canadian company. It's founded in 1989, and they make alarms, just like this one. Of course, usually they're installed in a building. This is just a portable case for demonstration purposes. I guess they didn't envision this kind of demonstration when they made this case. So it's modular security alarms, and they have 3 different kinds. They have the entry level called Spectra. They have the high security and access system called Evo. This is the one here. And they also have Magellan, which is wireless. And these days you don't want to ruin your fancy apartment or fancy office with lots of wires. So what you actually want is usually using the wireless system. And it's on my to-do list to actually look at that, because I'm a bit worried about what I may find. Anyway, so I've chosen here the Evo, the high security and access system, for more challenge. So what does the system consist of? As only approximately 10 of you have actually used the system, I imagine that almost none of you have installed one. So the brains of the system may look like that. It's like a small board that's installed in some hard-to-reach place in a building. Right? It's a panel. And we also have some ancillaries which are not too important for our purposes, but without which the system will not be functional enough, right? Battery, power supply, siren to alert when the system is tripped, right? And for Paradox systems, we have what's called COMBUS slaves, devices that provide two-way communication. For example, a keypad. If you look at a keypad, right, we not only type in the code. In the keypad, we would also want to see the status of the system. So it happened to me numerous times. Maybe not this keypad here, which has physical buttons, but the other keypads that I have that have touch buttons. I press the wrong button and I don't have feedback because I don't see the digits that I've pressed on the screen. It's hidden. So it's important for this device to actually be able to show if the code is correct in the end or not. If the system is armed or not, if you have movement or not. So it's two-way communication. And they also provide some fun modules that you can use, like expansion, printer, listening modules. This is a printer module. You can connect parallel port printer, serial port printer, and a USB printer to the COMBUS, and then you can print your logs live or whatever. There's also a listening module, which is a fun one. You can call into your alarm system remotely, or your company that installed it can call into it remotely and listen in what's happening in the building or wherever that module is installed. So that's an interesting one they have. But anyway, we're working with COMBUS here, but of course, no alarm system could work without the so-called zone interrupt devices. Those are the sensors, so to speak. Passive infrared sensors, tripwires, and so on, right? You've seen those on doors or windows, for example, or these over here, right? So basically all it does is it measures resistance of the connection of the circuit, and as soon as it changes to a predefined level or a different level, it will either trip the alarm or trip the fault, meaning that sensor has been damaged. And either of those would result in alarm and security company coming in if the system is locked at that specific time. But hacking these systems is at the sensor is a bit hard because they measure resistance, and trying to switch quickly enough, like removing a device and replacing it with a fake sensor that's always safe position, you can't really do that because of the timings. So there are other things you can do, and we're going to take a look at them here now. So this is the device that we are actually using here. It's EVO 192. one of the highest that they have. They also have Evo HD, which is a bit newer model, but this is the second best they have. So it has 192 zones as a maximum. That's where the name comes from. So what do we see on the panel here? We see the input ports for example, power supply. That's where we connect it to the mains. We have the battery connector, right? Because we don't want the bad guys cutting off the power and getting in. We want the system to still work for some time after the power has been lost. And a real-time clock battery for the clock, so the date is correct. It literally does nothing else. It just keeps the date correct. And I don't have it on my system for travel reasons, and that's why I have the trouble saying there's no RTC battery. The COMBUS. This is what we are discussing here today. So the wires from here will go to all, smart devices, but not IoT kind of smart devices, right? Smart devices where we have feedback, where we have two-way communication. And zones will happen here. See, Z1 to Z8, these are the zones. And we can expand them, of course. For an attacker, or should I say for an installer that installs the system, there's also a neat connector that you can use to connect to these 4 pins. It's called service keypad. If you actually get to the device, you can plug that right in and you don't have to fit all these wires like I did here. But we're going to do that because, we are simulating an attack. We also have a serial port, the classical one. It's usually not connected. And we have memkey port. This is a fun one. You can connect a special USB flash. It is a special connector. Flash drive, and it will copy all the configuration into the flash. So that's an interesting one, right? If you get your hands on the panel. So, the radio part, the one that I can't demo here today, but the one that I still want to talk about a bit. So, this is one of the remotes that I have, one of the top-level remotes. It's a two-way communication remote. It also has feedback. They have a bit cheaper remotes that not that featureful, but this one here, it has feedback. It has LED over here, and it actually can light up the buttons as well in different colors here. So when you press a button, you can see feedback. So naturally, I thought, how does it communicate, right? Where do I get it? What would be the first thing you'd do if you want to reverse a radio frequency device? So most manuals online talk about getting to FCC website and looking at the FCC ID, and then you get the spec. Now the thing is, Paradox is a Canadian company, and even though they sell their stuff to the US, apparently they custom tailor make it. So this one has been sold to Latvia, not to the US, and I couldn't find an FCC ID anywhere. So I had to do it other way. I opened it up, looked for the FCC ID, of course. Nothing there. This is everything that we have in there. We have a battery. We have a couple buttons, a bunch of LEDs, some more LEDs over here, and 2 chips. There's a really ingenious thing that doesn't have anything to do with this, but it's really so imaginative that they made it. So the battery connector also acts as ground for the speaker. There's a speaker on the other side, and it connects via the battery connector, one of the 2 terminals. That's quite ingenious. Anyway, so what we see here, we have programmable controller. So a microcontroller here, it's an 8-bit one. It's not, it's not too powerful. And we have a transmitter, transceiver actually. So it can transmit and receive on a frequency of developer's choice between these 2 frequencies. So what we do, we look up a spec sheet and we listen in. And when we listen in, this is what we see when we press the button. So hopefully some of you have worked with radios before. What we see communication around 433.9 megahertz. And we see some echoes of it to the left as well. So this is where the main communication happens. But we have to look closer to actually understand what the protocol is, right? So, by the way, hacking is all about learning new things. So in case you want to go into there, this is from a program called GQRX, right? You can take a look at that if you're hacking radios. So this picture here is from URH, Universal Radio Hacker. We go in closer, we tune on the frequency, and we take a look at how the specific frequency looks, how the amplitude on it looks. This is how it looks. I press the button 3 times here. So it's 433.9 megahertz, and I see that transmit and receive shares the same channel. How do I see it? I see it because of this spike here. If I press the button with the system turned off, I don't get the spike, I just get these 8 packets sent, right? If the system is on, it replies, and it's a more powerful transmitter because it doesn't work on a small battery. And we see the reply. There's one reply from the system, right? So that's what we see here. Now, we need to look even more closely, as South Park said it, and we have to look at the data inside. So when we zoom in, this is what we see. So one of those 8 bursts, this is how it looks. This is the beginning of it, right? It's a bit longer. I just didn't want you to copy my key, so I just included the first part. And we already see something similar to those of us who have worked with radio, right? We see the preamble here, for example, 0, 1, 0, 1, 0, 1, 0, 1, right? And then some ones and zeros. So it looks quite simple, right? What we see is one level amplitude shift keying, meaning that when transmitter is on, it's a 1. When transmitter is off, it's a 0. And the bit length, if we zoom even more closer, is 200 microseconds, right? So that's just this part here, zoomed in. We have 1, 0, 1, 0, 1, 0, 0, a bunch of ones, and so on, right? So that's how it works. Well, unfortunately, this is about where I have to end this part, since I can't show the demo. But so the structure, the init is 4 ones. This is just for anyone who may want to carry this further on. Synchronization preamble, 12 sets of 0 and 1, and packet length. So data is 120 bits. So I will return to this in a country that doesn't forbid import of radio equipment that's not quite licensed, and yeah. But for now, let's look at what I actually can demo here with you today, and it's an attack tool. Before the demo, let's talk about it, how I made it. M5 stack is what I decided to base my attack tool on. So once again, if we go back a bit, then what I had in the previous iteration of this research is I had my laptop, I had some wires going to the laptop via an Arduino, and I was able to see what codes user would type on a different keypad. Now, this time, I have my laptop over here and my attack tool over here. You will see that on the screen in a minute or two. And it doesn't require a laptop anymore, so it's much more, easy to use, much more concealable. This is M5 stack. So it's 5 by 5 centimeters, and the heart of M5 stack, anyone heard of or used M5 stack? Okay, you can try it out for prototyping. It's quite good. The only bad thing about it is the power consumption when it's off or when it's idle is terrible. But other than that, it's quite a neat device. So ESP32, which means basically Arduino, Wi-Fi, Bluetooth. We already have a bunch of stuff, right? We have antenna, of course. We have button. We have USB-C connector. We have Groove port. Here we have micro SD card connector here. We have a speaker even, and we have an expansion port where we can stack it up. That's why it's called stack. We can stack up different modules one over another, and that's how it looks. So it can be stacked up quite high. On the front we have display and buttons, so it's quite nice. Device for prototyping here. I think it still has power here for me, so that's good. So how I did it. The COMBUS, the one we already discussed, the one we saw on the panel, in the back of the panel, the picture that we had, has 4 wires. It has red, black, green, and yellow. And these are the layers of COMBUS that I myself decided upon, because there are no official specs for COMBUS. Maybe they are if you sign an NDA. I did it all reverse engineering from zero, so maybe those are different. But this is a bit similar to how ISO OSI standard for the network works, right? We have electrical layer, signal layer, packet command, and payload layer, right? So, looking into electrical layer, it's quite easy. We have, of course, our 4-wire bus. We have black and red for ground and power. This is the keypad here. We can connect over here, of course. Yellow is clock and green is data. So that's how far I've got, right? Here we can see an example. Any experienced engineer will immediately tell you that this looks like a clock. The yellow one and the green one looks more like data. But the thing is, it's also a two-way communication protocol, remember. We need the keypad to be able to receive the status of the system, not only receive the code or commands, not only send the code and commands from there. So how it works is that clock is used both parts of the phase. When it's high, then slave is able to communicate, and when it's low, then master is communicating. So depending on the clock here, the respective bit is who is communicating. And this is how it works. Master pulls up to send 1, and slave pulls down to send 1. So it's a reversed scheme in such a way. So this is the hardware setup here. This is our F5 stack. This connects to our COMBUS. So we have black wire, green wire, and yellow wire. It just connects directly to COMBUS. And, well, it's not as neat as I wanted it to be. I still need to order one more expansion board where I can solder the resistors. But basically, we have a couple of resistors there. For those of you who want to repeat this, and the code will be published on GitHub in today or tomorrow. So what we have here, we have the ground is connected via a 300 ohm resistor, and I have to warn you that the resistor values still need fine-tuning, but mostly it works. So it's isolated here so that as not to interfere with quite a sensitive protocol. And then we have a pull-down resistor here between the green one, the data line, and the ground, because the Arduino inside here it cannot provide enough power to actually do that by itself. But this works quite neatly. So, and when we actually intercept the packet, this is what we see. When master, the panel communicates to the keypad, we can see commands like this, right? For example, here we have a command byte, we have command content, and we have the checksum, right? Or here we see the panel sending in time. It just sends clock all the time to all the keypads. This is the default packet that it sends every pulse if it has nothing else to send. The slave, on the other hand, here is channel request command. It basically says, I want to talk. I'm the keypad or whatever, and I want to communicate. Please let me communicate, right? As you notice, the length is the same. So master sends this, slave replies with this, for example. And this one here is a command where slave enters the pin code. It says, okay, so I want to enter pin code, here's the code, this is where I'm from, and here's the checksum. If you want to take a deeper look into how this is made, you can pull up my old presentation, and it's all in there. Now for checksum, it's really a checksum. So it just sums everything and takes modulus 100 in hex. So it's super easy, right? And checksum, of course, I should note, begins at the yellow one, right? It begins at the yellow byte. It doesn't include what's before there. So now that we have that, let's look at payloads. The payloads that I discovered, they have no encryption for this high security system, for this Evo 192. Text is usually fixed length, often 16 bytes long, and 020 or space character is used as a filler, right? For example, here we can see panel informing all the keypads that there is a zone called door01, and here it is, its ID, right? Numbers are usually packed binary coded decimal, so that is quite easy. And there's one more hack. So 0 in a number is usually converted to A. In BCD, you know, if we have a number, for example, 29, then it would look at hex as hex 29 on the channel or in the data. Here, if the number is, for example, 20, it would be 2A instead of 20, right, in hex. That's what they did. But, so at least we have obfuscation, even though there is no real encryption. Let's now take a look at demo. So, yes, please come here. So, let's see, yeah, let's start there. Yeah. No signal, huh? Oh, nice. Perfect. So, this is the M5 stack over here, yes. So, you know, then we have everything over here, and the cable here goes to the keypad connector, right? And the wire goes into the panel. And the keypad is connected to one end. So what we are simulating here is that we have a keypad that is not used, that is abandoned, and an attacker manages to connect to it. And without interrupting the functioning of the device, the attacker leaves the device attached over there. And no one uses that keypad, so no one notices. And we have other keypads over here that are the ones actually being used. Right? So for example, if I were to type in a pin code, then if you look over here now, luckily I programmed it to repeat itself if I press this button here. It registers the pin code that was typed, and it also shows it in red, meaning that it was an incorrect pin code, right? So let's now type a correct one. Let's hope it is a correct one. Okay, and it is asking me what way I want to arm. I'll say I'll stay in. I'll be staying inside, and it's arming it right now. And we can see here on this keypad over here, it's exit delay, right? Now over here, hopefully, if I look at the last code sent, we see it's green, so it was actually accepted by the system. And this module knows that. And so that's the first part, right? We have it here. It remembers the last pin code typed in, and that's how it works. Now, we will return back to a different demo after some more slides. The system is meanwhile arming. So, this is basically, I just took what I had in my laptop, the code I had in there, and I moved it into the High stack. Nothing magical, even though it's a nice device that you can actually go and sell on the black market somewhere. Not that I would do that. But I did want to do something more. I wanted to actually, for attacker, to also be able to use this device to talk to the system. Not just listen, not just see the codes that have been used, but also send its own data. So the question, of course, is why? Why would we need that? What would be the use of this rogue device sending in some data? Well, one thing I already mentioned, if we want to brute force, let's say, a code slowly, we can do that. The device has a clock in it. It's not RTC, I think, but it has ability to count time, and it can time the attempt and test, let's say, 100 codes per day, right? Which means in 3 months, we got at least one valid 4-digit pin code. We can also do protocol fuzzing. Now, all these devices here, all the keypads, they are made by the manufacturer and they adhere to the protocol precisely. And as you know, one of the problems with protocols is that the developer usually thinks that they're closed. This is my device. It doesn't have to be hardware, right? This is my web page. It will send me this HTTP request. It will have this form data in it. And this is my server side. It will process that data. And it's all closed ecosystems. Then a hacker comes and makes their own web page that sends different kind of data. So not unlike here, the developer thought, of course, we have these devices that communicate. But with this device here, we can actually try to fuzz the protocol. We can try to put our own data, see what happens if we send a packet with all zeros or all Fs and so on. We also can do replay attacks. So we can just, for example, record that something is happening. We can record the whole day of people moving around the building. And then in a press of a button, we can actually replay that to the system. And the system will think that the movement is the same. For example, on Sunday, right? You record Thursday, and on Sunday you press a button, and the system logs all the movement even though there's no one there. And maybe open source keypads, right? If we want to, instead of using a closed source one from the manufacturer, we can actually build our own keypad as well using this. So the question here is, can we do that? And yeah, the answer is, of course. That is why I'm going to show you the demo here. So let's hope that works neatly as well. So let's put it over here. So we can see here it says stay. That means it's stay armed, meaning that if I were to open a door over here, it would the alarm would sound. We don't want that right now, at least. Let's try to disarm it at first. Let's move over here. So we have our attack device over here, and we will press the middle button, and let's hope it works. This is the first time I actually made a recording of my live demo. I never do that, but this time it's also finicky that I have a video if it doesn't work. Let's try that now. Nice, it's green. If you look back at the panel here, it says disarmed. So we managed to unlock the system just by pressing buttons here. We can try doing that again. Let's see. Let's lock it down. Let's use this arming here. So it's arming now. You know, when you exit a building, it does that, so you know how much time you have left to arm it. Okay, move it over here again. Let's see if we can cancel that arming. Yeah, and we cancel the arming as well. So this is how it works in a nutshell, right? And I haven't tested it, but I think even if you would so even if you would trip the alarm, oh, I shouldn't have done that. It's let's disarm it. Let's use the other one that is not so noisy. Even if you trip the alarm, you should be able to actually close it off and cancel it using this device, which I'm going to try in a second, but we don't need the camera for that. So that's for the demos. If you later on, you can come on and take a look around all the hardware if you want more. But I still have some stuff to tell you. And the next topic I want to talk about is firmware. Now, for firmware, as I told you, I did some preliminary work to see if it's possible to reverse engineer it. And I'm committed on continuing that work. But it seems it might be a bit hard. So this is how this is a close-up of the panel. We see some chips that are quite telltale here. And we're going to talk about what those chips are and what to expect. But before that, so our system has armed. Now it is locked, right? It's instant locked. Let's try to open the door and hope that we don't have too much noise from the system. So I'm gonna simulate opening the door and the alarm should go off, right? Yeah, okay. So alarm goes off. I'm gonna try pressing the buttons here again and yeah, nice. So I didn't test that one before, but even that works. Nice. So, okay, back to the firmware part, right? We have these chips over here. What do we see? I ordered them by the size of memory, right? So, first of all, we have this real-time clock chip over here. It has 56 bytes of non-volatile RAM, so nothing too interesting. Specs say that it only actually stores information related to the clock, so we shouldn't expect to find much there. Where else could data be stored? So what we're looking for are two things. We're looking for the code that they made to actually take a look at how it works, if there are any possible bugs, do reverse engineering and code analysis on that. The other thing we're looking for is configuration codes. All right. If we were able to, say, get the 6-digit installer code, we might be able to actually attack the system, reconfigure the system as we want it. So the next one here is an EEPROM. It's 32 kilobytes. Page size is 64 bytes. So in 32 kilobytes, we already can store enough. So that might be one of the memories where user data is actually stored. By the way, important note, when programming the system and you use a graphical panel like one of these one, it's quite easy. If you use a classical panel like this one here, for example, right? All you have is a small screen and a bunch of digits, and you program it using a programming sheet. And it says, for example, if you want to add a new zone, you write to this address this number, right? So basically, we already have all the addresses in the installer's manual, so maybe they will match up. That would be nice. There's one more EEPROM. It's 2 times larger. It's 64 kilobytes. Located right over here. But the hard part is actually the microcontroller. The microcontroller is Renesas R5F, and it also has memory. It has 128 kilobytes plus 16 kilobytes of memory. Luckily, according to the spec, it's read-only memory, meaning that at best, all it stores is the code. It will not store any configuration because of it being read-only memory. It has a 4 kilobyte flash though, but then again, I guess that is why we have the EEPROMs here for user data to be stored, not the flash in here, and it has 12 kilobytes of RAM, which is average for an embedded device, right? Some devices have a kilobyte, maybe 2 kilobytes. This one has 12 kilobytes of RAM, so it can run some reasonable code. Now, what we might get from that, we might get the code that actually provides the radio communication, because that is the unknown part right now, how to fully replicate the radio, how to understand what's inside instead of just doing a replay attack. So next steps here are known, but they are not easy. So dump the data using a bus pirate, use radar2, my favorite reverse engineering tool, and probably it will also involve coding missing support for the processor, because as far as I see, radar doesn't have support for Renesas R5 instruction set. So I might end up having to code some plugins for radar, which I'm not really looking forward to too much. But at the very least, what we can do here is we can pull out the data out of the EEPROMs, and the data being data, we can take a look at it using programmer sheet, and we can actually fetch some useful information out of there. So in summary, I had to put this slide in here. This is a quote from their webpage. Digiplex and Digiplex Evo systems provide the highest level of protection for banks, high security military and government sites, luxurious residential homes, and any place where maximum security is essential. This is text that you can get when you click on the name of the panel in their webpage. So that's the high security you get, right? No encryption, no nothing, and unlock it easily. So what has been done? Results. We created an F5 stack attack tool based on F5 stack, right, for this Paradox COMBUS protocol. It also supports active keypad emulation. It will be expanded to do more. Right now it can unlock the system from whichever state it's in. We tested some RF attacks. Some are successful, some are not. Sorry again that I couldn't demo it here today, but I look forward to actually completing the other RF attacks as well. Firmware reverse engineering is unlikely because of the, well, esoteric processor, let's say so, not too popular in reverse engineering community right now. However, EEPROM can be read, and that's what I'm going to do. Speaking of what I'm going to do, the tool over here, right? If I take it, it's not too modular. It's much better than it was before, but you know, it still could use some improvements. So I'm gonna probably make it more modular and eliminate this part and put it inside. That's one thing I'm looking forward to doing for the next. I'm gonna try to find the right resistors so that it works 100% of the time, not 90% of the time. Continue testing RF attacks and pull configuration, including installer code and other codes from the EEPROM. Finally, COMBUS over radio. Now, if anyone wants to sponsor me a similar kit for Magellan, the wireless system, I'd be happy to take it and then do a presentation on it, because we looked at COMBUS here. I showed you what's inside COMBUS, and you saw that it's all mostly unencrypted. And there's an attack tool for attacking COMBUS. Now, COMBUS, as you remember, is the protocol that connects a keypad with the panel. In a wireless system, the keypad, as well as all the other devices, are connected wirelessly. The question I have is, that I don't have the answer to yet because I don't have the Magellan system, is if the protocol is the same. Have they actually taken this insecure protocol and made wireless? So that is the question that I have, and that is something I'd really like to take a look at. So slides will be available on my page today. Tools are available there. It will be updated in a couple of days. And also, as I said, I'm on Twitter, and you can follow me for other conferences or for other presentations over there. Kirils Solovjovs also has a bunch of slides from all over the world where are given different presentations, different topics, including some on this topic. So I think we have just maybe time for one or two questions, if there are any. Okay then. You're welcome to come here. I have to let the new speaker come set up, but we have 2 or 3 minutes to take a look at this here if you want to. You can come talk to me, and thank you once again for being here.